So fantastic to be here today. At the end of 6 months worth of work, I took early retirement from a large equipment manufacturer for drilling, and Tara was there literally about 3 hours after I'd retired and said, "Oh, I've got a job for you." And so my retirement was literally between about 4 o'clock in the afternoon and 7 o'clock in the afternoon at the conference in Nevada. So thank you, Tara, for shortening my retirement amazingly. Yeah. No, I was never going to retire anyway. But so let's have a look at the drilling challenges that we have. Yeah. So if the first big one, and this is the one that Rebecca is going to go into in a lot of detail, is ROP generation. Yeah. And ROP generation isn't unique to Superhot rock, but every day that we reduce the time that total spread rate operation is on location is massive savings to us. Yeah. So if that rig and all its equipment is 150,000 euros a day, and we reduce that by a significant number of days, then that well cost is coming down. So ROP generation is ultimately very important for how we improve the economics of Superhot rock. There's been some really cool innovation going on literally in the last 3 years, and Rebecca will look at some of those transformative technologies that have changed what's happening in the rate of penetration. And there's some really new groundbreaking technology that's coming out to follow on from that, but has a much lower readiness level. Temperature management. So we're going to drill these wells at up to 400, 450, 500 degrees centigrade. How are we going to get have ourselves the ability to steer a well in a particular direction to potentially create an enhanced geothermal system reservoir? We have to have the well pointing in the right direction relative to the principal stress. We have to have it at an inclination that makes sense to be able to do some sort of secondary process to give us an enhanced reservoir or an EGS type system. So to do that, we have to be able to get data up from downhole. We have to be able to steer the hole. So there's two ways that we can come at that problem. One is to come at it with higher temperature tools, higher temperature motor assemblies, higher temperature downhole equipment. And the second one is to change the environment that those tools are living in. So as we improve the environment that they live in, and we drop that temperature, we're going to see slowly an improvement in reliability. So what we want to see is those two things come together: dropping the circulating temperature of the wellbore and raising the temperature of the tools at the same time, so that we can go through that process. So I'll cover that in a bit more detail. So our first big challenge is rig capabilities. Yeah? So these wells are either going to be, in Iceland, we're talking really probably only 5,000 meters to get to these sort of temperatures, even lower in many cases. But in a lot of the world that Tara put up on the map, these temperatures are not going to be there until 7 to 10,000 meters, maybe even deeper, maybe as deep as 15,000. So to be able to pump the fluid down the hole, rotate the pipe at surface, and run a deep 9 5/8 or a deep 7-inch casing string, we're really going to have to say, what is our objective for this borehole? Where are we going to have that temperature that we need, and engineer from the bottom up back to the rig? And when I started looking at the rigs capable of doing this around the world, it is not very many. Yeah. You're talking about something like Doyon 26 that's drilling in Alaska at the moment, that has basically the capability of drilling 50,000 feet or those sort of depths. Yeah? In their case, they're drilling very long horizontals because they're drilling an offshore oil field from land. Yeah? So that sort of capability is what we're going to have to look at. We have to have enough pump to be able to get the flow down the hole. If we're going to have big pumps, big flow rates, we're going to have to increase the standpipe pressure capability of the rig. But some of the really neat things we need to do, that when I looked across the fleet of rigs, is clever application of electronics. So we really need to have electronics put in the right place to have that micro control of the on-bottom environment. You know, can we have very small, accurate changes in the line coming out so that we have nice controlled ROP going on the wellbore? So we want to be able to potentially have managed pressure drilling. How are we going to completely change our fluid and drill with carbon dioxide? If we have a carbon dioxide system, we're going to have a degree of managed pressure drilling to manage the state of the carbon dioxide, so we can change from liquid state carbon dioxide to gaseous state carbon dioxide. Particle impact drilling, which I was personally involved in, we did that out on Forge, where we fired, shot down the hole, circulated it up, but still there were little particles coming out of the well 3 weeks later. So how do we have the ability to capture all those particles, get them on the middle shaker, and keep that wellbore nice and clean? And then robotics. We may have tools and equipment. Even if we've managed to cool the wellbore down, are the drill collars going to come out of the ground so hot that they would literally burn the rig floor hands? Yeah. So can we manage that whole process safely and efficiently with a relatively low-cost robotic system? There is robotics now that can be put onto an old existing rig with a couple of $1 million upgrade rather than a $40 million robotic rig. So the smart use of money in the right places. Yeah. So on the rig side, the TRL level we believe is 9. Those rigs are out there. The technology exists. It just needs to be pulled together. Taking the best top drive from an offshore rig that's drilling super deep, putting on a fluid system that is coming from Sakhalin Island or Alaska, combining that all together to provide us with the equipment that we need to drill at these depths. Yeah. So I'll take a step back, and Rebecca's going to carry on, and she's going to talk about everything that makes ROP.
Thank you very much, and it's great to be here and be able to present the work that Tony and I have been very focused on for the last 6 months. So, as he has shown, there is a lot of components to this machine of a drilling system, a drilling rig, and you need every single component to be rated to SHR capabilities, or else you will not necessarily have a successful operation. So, how does drill bit technology fit into this? And as he's already described, it is related to the rate of penetration, which is related to the economics of a geothermal project. You want to reduce the number of drilling days or as well as non-productive time. So doing this, you need to improve your rate of penetration into hot hard rock domains, which is not typical for conventional traditional methods. And you also want to improve the bit longevity so that you are reducing your trip time, which is a non-productive time. So in the past, we have typically used tricone bits to access conventional geothermal systems. Recently, that has progressed into polycrystalline diamond cutter bits, such as the one that's in the middle. And so we're going to explore what else is out there, or what combination of these systems could be used to enhance our ability to access these domains for super hot rock. So the farthest ahead is undoubtedly conventional rotary drilling. So here on the right, you can see the Baker Hughes Volcanics geothermal line, which is rated to hard rock drilling. It is high temperature rated as well as for hard rock, and they have both a PDC cutter, a tricone, and a hybrid. I believe they were used here at IDDP as well. So ways to improve your ROP and bit longevity include the cutter and bit design, as well as MSC management, so mechanical specific energy. So that's sort of a diagram on the far left shows that if you can increase your weight on bit, you may increase your sliding distance and reduce almost the amount of time that the bit is in contact with the rock. It's also very essential to reducing or mitigating against bit dysfunction, such as stick slip or bit balling. And this can be done. Forge's approach has been to do extensive training of their personnel to make sure they understand the physics of what goes into drilling to improve their education on how to mitigate against these issues. It can also be done with automated drilling, and they have done some experimentation on that, but that is sort of a gap that needs much more proof of concept, and it has a lot of potential for improving the efficiency of downhole, or the conditions downhole. Also, temperature management, very essential to cool the drill bit to reduce frictional wear or frictional heating, and this will improve your bit longevity. And this can be done with the configurations of the nozzles, which is sort of that the NOV read hike-log system does that sort of pre-drilling operation modeling to be sure of where you want to place your nozzles to reduce the frictional heating. Some other aspects of conventional drilling that need to be addressed are the alternative cutter designs, such as conical diamond element bits versus round cutters, or square cutters, and the conical shaped ones are potentially better for interbedded formations. You also want to improve your steerable systems, your rotary steerable systems in your deviated wells, because you want to reduce the frictional drag, and to do this you need to have very uniform wells. And as you can see this is the forge log, and you can see that the rotary steerable systems were much more efficient at keeping the hole straight. Speaking of Forge and Fervo and some of the more frontier pilot sites, we have seen massive improvements in ROP generation and performance. This is from Fervo, their Fervo project at Cape Station, Utah, and you can see from progressing from well 1 to well 8, the total days drilling has been reduced from 70 to 22. So this is about a 70% increase in your performance and your rate of penetration. And I do want to highlight, and this is done through iterative drilling, and every site is unique in its own way. So how do you optimize this globally or universally, and per your geological setting? So one thing I want to bring out is that there does seem to be a trending limit. This is not necessarily the limit. I think there's a lot more innovation that can happen that will continue to decrease the amount of time we're on site, but I'm going to refer to this as a potential issue to consider down the road. In terms of performance of the drill bits, you can also see but the black diamonds are the number of drill bits used, and again, progressing from left to right, it is from well 1 to well 8 at the Fervo station. You can see the improved, and the bars are the lateral footage per bit, and they are increasing. So your performance per bit is increasing, your number of trip times is decreasing. So this is great performance from Fervo achieved. This is from ELSADI 2024. This is this year, so you can see that the performance is, and the advancement is happening at a very high rate. So technology gaps for conventional drilling. Roller cone is at a TRL status of 8 to 9 with performance limits at high temperature due to elastomer seals within the drill bits. PDC cutters are at TRL 9 to 10. They have been used in supercritical domains. They've been used at Forge and Fervo as well as in IDDP. We want to scale these systems up and continue to increase their temperature limits and their ratings, particular specific, and this can only be done with rapid iteration. So one missing element in this process is access to SHR domains. So we do need to have a internationally accessible location where we can perform this iterative improvement. This is going to require collaboration between major drilling firms, which can create maybe some issues considering IP or trade secrets, but there are ways around this. And then you want to improve your deployment of metal to metal, so elastomer-free borehole assemblies to increase your temperature ratings, as well as reduce friction in deviated wells. So conventional drilling is originally for hydrocarbon or mineral exploration, but they are adapted for hard rock drilling. So some of the hybrid conventional systems we look at use rotary drilling, but have an additional component of it that takes advantage of the brittleness of the rock. So basement rock is brittle. It will fracture if you impact it with enough force. So these three systems, we're going to use that sort of concept to their advantage. And the first one, which is probably the most mature, is percussive. So this is literally a hammer, or air hammer, or a fluid hammer, as it's referred to. And it just is smashing the rock as you go down. This creates fractures, it de-stresses the rock, and that improves the efficiency of the rotary system, the rotary component. This has proven high ROPs, almost competitive with conventional systems at 20 meters per hour in locations such as in Australia, and that was in hard rock, not necessarily hot. And some of the other pioneering projects are Hydrovolve, based in Aberdeen, as well as the EU Horizon 2020 Orchid project, which is a combination of rotary, percussive, and water jet, which I'll go into next. One of the challenges expected of this is delivery of power at the bottom of a well, especially as you increase depth. So water jet, similar concept, but instead of a mechanical sort of vibrating or hammering mechanism, it is using fluid jets, very high pressure fluid, to create these craters in the rock that it is effectively de-stressing the rock and will improve the excavation rate from the rotary component. This has been also adapted from soft rock lithologies, and you can see in the drill bit on the left, it has nozzles attached to a roller cone. And these are less experimented for hard rock drilling, but there is still potential that it should be explored. And the Orchid project is specifically for geothermal projects in hard rock. So following that, similar, as Tony has mentioned, particle drilling. Rather than water, you're firing steel bullets or BBs or particles down hole. This impacts the rock and de-stresses it, and then you have much more improved efficiency at drilling the rock. So NOV did test this at Forge, which is that's being the first image shows their deployment at the Forge site. So they are at the state where they can be deploying in field. Maybe the first couple attempts were not as successful as they were in other locations, and then this resolved in it just being an issue in the configuration of the nozzles. So again, we have to emphasize that this needs to be iteratively improved by in-field experimentation. And there has also been testing with Canopus, which is another Netherlands-based company that is also doing particle drilling. So general technology gaps, percussive drilling is at a TRL 8, water jet is at 7, but 3 to 4 for Superhot rock. It's not been heavily invested in up to this point. Particle drilling is at TRL 6, needs to be deployed in field more often, as do all of them. So similar to conventional methods, you are at a state where you need to be doing in-field experimentation and in Superhot rock domains, and it would be best done in parallel, to conduct parallel drilling campaigns with conventional drilling systems so that you can compare the performance directly. And one of the main concerns for this is the transmission of power to the bottom of the bit. Maybe not so much of an issue with the water jet or particle issue, or particle systems, but for percussion it will be. So lastly, I mentioned the limit that in the Fervo drilling results for their Utah State site. Again, that is not an actual limit. It is just something we should anticipate as we start to get into deeper conditions, or as we go deeper. Any performance gains we make in ROP may be lost in the trip time, which are going to get longer as we go deeper. So are there other methods of just rock excavation and destroying that we haven't considered, that are not mechanical, that do not need bit replacement? And one new area of considering this is direct energy. So direct energy is the transmission of not necessarily heat, but electromagnetic or electric energy downhole, which will destroy the rock, and you have far fewer bit, like me. You don't need as many bits. You don't have a bit, so you don't have to replace it. So the advantage is less downhole equipment. So plasma drilling is being pioneered by GA Drilling, which is based in Slovakia. They are also doing it in support with Neighbors Industries based in Houston. Technically, you're just firing a electric current onto the rock, either directly contacting it or with a small separation distance. You need dielectric fluid in the well to transfer this current, and it vaporizes the rock by basically, as soon as this current enters the pores, they explode. So they have a solely plasma bit technology, which is, could be 3 to 10 kilometers, and then their anchor bit is a combination of conventional drilling methods with plasma. So some of the challenges are, again, transmitting power to the bottom of the well, but this is already, since making this presentation, being overcome with a downhole alternator that they are attaching, so things are evolving very quickly. As well as clearing the conventional drilling borehole fluid, because direct energy methods do not work for sediment and soft rock. So you would have to use conventional drilling to clear the overburden. for deploying these systems. So that's shared between both plasma and millimeter wave. So millimeter wave is a little bit different. Rather than an electric current, it is almost like a very, very high-powered microwave. You are just shooting very high-intensity electromagnetic energy downhole through a waveguide, and this is going to vaporize the rock through a dielectric excitation. So this is being pioneered by Quaise Energy as well as MIT, also in support with Neighbors Industry to ruggedize their system. So again, and one of the biggest challenges for this system is deploying a waveguide because it must be straight. If it's bent, then you're going to vaporize your waveguide and the metal system is going to get stuck. You won't be able to progress your hole downhole. And so this is one of the things they're looking at. They are also still laboratory based. They need a 1 megawatt gyrotron to power the system, and those are very rare. I think they have maybe a 1 or less than 1 per gyrotron produced per year. You also need to ruggedize the equipment. Well, okay, so the technology gaps for both direct energy and for plasma and millimeter wave is you have a very specialized apparatus that need to be deployable on a rugged drilling rig and operable by drilling rig personnel. So how do you make this transferable? How do you scale this is sort of one of the gaps, but you also need to bring it out of the lab and into the field. I think they are still in a modeling and laboratory phase, although plasma drilling is a little bit closer to infill testing, which they'll do within a year and a half. They need rapid iteration similar of improvements, similar to conventional drilling. And they also need further synthetic testing on rock properties because a heterogeneous rock is not necessarily going to melt or be destroyed uniformly, which is really important to creating a straight hole. So for example, millimeter wave, if you have a rock with different components of silica in it, then it will melt heterogeneously, and therefore you are going to have issues with progressing your system downhole. And I will stop there because I think there's a whole other part.
Thanks, Rebecca. How much time do I have left? Just 5 minutes. Oh, we're going to have to be quick. Yeah, I've not been known to be quick. Yeah, so let's speed this up then. So for temperature management, the first thing we really had to think about was, rather than thinking of individual components, think about it as a total system. Yeah, so good engineering, the right rig. How do we model that temperature? And it was really interesting when we started to get into that temperature modeling that we really thought that with a combination of technologies, we could deliver 135 degrees centigrade water to the bottom of the hole at 400 degrees C. Now, that may be a very expensive solution, yeah? So depending on how we do that, but we actually think that temperature management with a combination of high temperature tools and a complete system approach, thinking about geothermally differently. Can we drill bigger holes? Can we use bigger pipe, higher flow rates? We push that. But if you don't insulate the total system, then the photo is applicable. So you have to think about what is going on in the tool joints. If you have no insulation on the tool joints, you're going to lose half your heat out through the tool joints, even if you've insulated the tube, yeah? So if we now look at the tool capabilities, yeah, and it's really interesting when we went to MIT in the Lincoln Labs a couple of weeks ago and started to see electronic and silica capability with fully depleted silica. There looks like there's a pathway for tools being able to get up closer to the 300 degrees C range, yeah. So if we've seen in looking through the whole range of tools, the top range at the moment is 210 and going to 225 through HEFI. And then the other providers have ranges of tools between 175 and 200 degrees C, but with LWD and different measurements, yeah. The good thing with some of these is some of these tools and electronics are going into rotary steerable tools as well. So we're lifting up the temperature profile of rotary steerable as well. So can we turn a corner and deliver what we need? Yeah. So if we look at the high temp tools, TRL8, if used with other cooling methods, yeah. So if we have the highest temperature tool in the hole, we can trip in as deep as we can possibly go with that tool. Then we cool the system and we stage in. And the combination of that with some degree of insulation and a high temperature tool means that we shorten our trip times and we reduce the risk. If we lose pump or lose power on the rig, we have time to get out of the hole. On the insulated drill pipe side, Drillcool had a commercial product that is insulation on the outside of the pipe. Unfortunately, relatively fragile, but you could do some clever things where you drilled with a downhole metal-on-metal motor and slid the pipe in the hole. So you're not damaging the Drillcool pipe. NOV, which where I left in October, we were in the starting to produce tubes for an insulated pipe, which is a tube inside a tube. So we took an old thread form and we looked at the thread that we needed to be able to press a tube inside. So we got a tube with a motor rubber on the outside pressed into the drill pipe. And then we modeled different percentages of that in the wellbore, and that's got us to the 135 in 400 degrees C rock. Very simple technology. It's just a tube, rubber, and another tube. So not a big jump in technology. Where the technological jump and the support from universities and labs could be, what do we put between the two tubes? You know, can we put crushed space shuttle tiles in between the gap and improve the performance of it? So on insulated drill pipe, TRL 7, need to get the NOV pipe manufactured out and tested in a well. Need to, you know, as Rebecca said, iteration is our most important thing. Drilling more wells, pushing that temperature and depth, so we test all of these things. A lower cost solution, but not going to drop the temperature to the same level, is using a low heat coefficient coating. So you put the pipe into a hot oven, spray in powder coating, and that coating has a chemistry with either nanoparticles and other components that drops the rating of that. When we worked on this last couple of years, we got it down from 0.8 down to 0.16 watts per meter Kelvin. So it is a big drop in big increase in insulative capability, but it's only very thin. So the runs that have been done in deep oil wells, where the temperature was 200 degrees C, it dropped it down to 175, 170 degrees. So it's that sort of scale. Yeah, coatings are are readily available today, but what we would have to look at is how can we raise the temperature rating of that coating to get us to a higher temperature area. Mud coolers, next component in the system. So we take, if we've engineered this complete system and we're still not getting to the temperature that we want at the bottom, can we inject the fluid into the surface at a lower temperature to enable that system to still deliver the temperature of the fluid that we get to the bottom of the hole. There are two major manufacturers for the geothermal market. That is Drillcool and NOV, but there are other companies manufacturing mud coolers in the market. Yeah. The drilling fluid. So we looked at drilling fluids, and the main driver for drilling fluids in superhot rocks is simple. Yeah. So either super clean water or carbon dioxide, so liquefied carbon dioxide. But as we drill these more and more challenging wells, we've got to think about high temperature lubrication. How can we minimize corrosion in the wellbore? Amplified temperature, amplified corrosion. So how do we get corrosion into the system? Yeah. Are there synthetic polymers or other materials that can get us up, giving us some gelling capability at higher temperatures? Yeah. So we're getting got to push things up there. So fluids is something that could really go out and get a lot of help from labs and universities. Yeah? That's the scale of projects that really suits them. You know, building large-scale tools or scaling up drilling rigs is not in their budgets, but good chemistry and good chemical science and chemical engineering could really help us push the drilling fluids. Yeah. So if we look at that, the additional benefit we can get from is simple well engineering. If we can create laminar flow in the annulus, if we can pick the drill pipe size and the hole size and create a circulation system that is giving us laminar flow for effectively no extra cost, we get an insulation layer being created by the laminar flow coming up the side of the annulus. Yeah? We get a big insulation factor from that. We get a big insulation factor coming if we have gas on the outside of the well. Many wells in Iceland have complete lost circulation. When you have complete lost circulation, you have an air gap between the pipe and the wellbore. Could that actually be engineered in as part of the system? Yeah. So fluid dynamics, flow rates, laminar versus turbulent flow can have a significant impact on it. Good solid engineering, just engineer the wellbore from the bottom up to get that. Fluid dynamics and going into carbon dioxide. So carbon dioxide has the potential to be used as a drilling fluid. We're not talking about, in my presentation, as a production fluid, but we can pump it down the well. Its changed state as it comes through the bit goes from liquid to gaseous, and we get a thermal impact on the formation as well. So if we're drilling with conventional bits, do we get a significant jump in ROP because we're breaking down the mineral structure of that rock that we're hitting with cold carbon dioxide? So carbon dioxide is being worked on and looked at as a methodology to be used in the United States in upcoming projects on the Newberry volcano. So it's going to be really good to see through an experimental process with lab help, taking that out in the field and seeing what the challenges are with carbon dioxide. So really, really good. Lastly, before I come to the very last slide, is there are other potentials that we can have by using something like titanium pipe. So if we talk about the challenges of getting all the way to TD, one of the biggest challenges in there is weight. So can we do a combination of titanium pipe for weight, coatings, regular drill pipe, flow rates and rigs, and combine all those together with 225-degree tools pushing to 300, and we get to this this point where we're at with super hot rock. So jumping from this, you know, there is lots and lots of scope for universities, laboratories, and places like Iceland who have super hot rock, but we're not going to have to necessarily blow this whole depth thing out the water. By using the high temperature environment that we have in this country, we can go through field testing rapidly, a lot of different products that have to survive in this environment. So I'm really excited to be here in Iceland and see this, the opportunity we have in this country to test things and test them quickly. So to close out, where after doing this work, when I started this work, this was not my conclusion. After I'd looked at all of this for the last 6 months and worked with a lot of really cool people out there working on this tech, I think we're at engineering iteration and not complete scientific breakthrough. Yeah, I think we can put a system together. I think a lot of people in this room who are part of this can put a system together, and we can drill super hot rock. We could probably go and do it with a few today. Yeah. So I think it's there. Some of the manufacturer of these things have engineered them but haven't produced them. So we need to get them. You know, normally most of those companies give them a PO and they'll actually make something. Yeah. So that's the state. So thank you for your audience today, and we'll take Q&A. Yeah. Okay. Yeah.
I'm going to take questions, and if nobody wants to start the bidding, I will ask the first question, but I'll give you a moment. Right, sorry. Sorry, you might have to speak loud. Hello.
Thanks, Tony and Rebecca. The comment you made about titanium, Tony, is very interesting because titanium, to begin with, has a thermal conductivity that is 1/3 of steel. On top of that, if you go with your coating, on top of that, if you do a couple of other things, I think you'll be getting closer and closer to your 400 degrees C target. So that is a good comment there.
Yeah, and sorry, really good question, yeah. And I think in the end, when you think about not only the materials thermal capability, but you have to think about the sort of bottom whole string design, yeah. So maybe the ultimate assembly is the latest and greatest PDC bit, even latest and greatest PDC bit with some plasma component to it potentially, or using the cold fluid that's coming through it. Then a heavy bit of insulated pipe, okay, which is working like heavyweight pipe to transfer weight to the bottom of the assembly. Then a component of titanium drill pipe, and then a large diameter coated pipe back to the surface. That may be the lowest cost system to get us down to these depths and temperatures. And yeah, I think titanium has got a component part to this system, yeah.
Susan.
So, Rebecca, you talked about the energy drilling methods and their aim being to vaporize the rock. I keep wondering, why are we trying to vaporize the rock? It takes a lot more energy. Couldn't we just break it down with these energy drilling methods? And I see that maybe that's what the aim of the combining the PDC bit with the plasma drilling or something. It's so much energy we have to deliver at the end of the drill string in order to vaporize rock.
Yeah, I think that's a totally valid concern. I think in the case of millimeter wave, they say you need a 1 megawatt source of power, which is a lot. But they justify it by saying in the course of the lifespan of the geothermal project, it will be something like 1 to 3%. But that also, in the conditions that they are in Superhot rock, and so you have to reach those domains to really validate the use of that much energy. But the plasma drilling is probably the hybrid bit is probably the furthest along in its sort of use case scenario. But yes, it is a lot of power. I think that depends. So far, millimeter wave, it's still very small. They're at maybe 3 to 5 centimeters. So I think the deepest they've gone is 8 meters down, and I think it's like a 1 to 10 ratio. So millimeter wave so far is quite a small bit, but plasma I think is still just a conventional, normal, I'd say 9-inch range.
Stick your hand up.
Okay, yeah. So. Yeah.
A conventional rig is going to be a 3 megawatt generator probably as well. So.
Yeah.
But Trenton's here from Quays, and so grab him at a coffee break if you want more detail.
That is also in the their experimentation so far has been with a lesser powered gyrotron than what they would deploy in a geothermal project. So once they do have that higher source, then they can drill much deeper. So I think they're acquiring one. If you can correct me, yeah.